Thank you, Michael, for the introduction. The room is not so crowded anymore. All the blockchain people left, apparently. Yeah, so I'm going to present a graph query language proposal called GCore. To introduce a little bit myself, I'm a graph database systems researcher from TU Dresden. And I did research on graph data management, schema evolution, schema flexibility, adaptive indexing, and other topics. And next to that, more industry-related activities are together with SAP HANA Graph and the OpenCipher project Stefan told us about earlier, and also the LDBC Graph Query Language Task Force, which is the entity who came up with GCore, which is the talk about the talk will be. What is LDBC? Some people may know LDBC is the Linked Data Benchmark Council, which was founded out of a EU research project, and it's a non-profit organization that is devoted to specifying benchmarks for graph database systems to make systems comparable in terms of their performance. And out of that work, or when you want to define benchmarks, you have the problem that you have to define queries, which are run by the benchmarks, and then you run into the problem that it's hard to do that for graph database systems because there's no standardization of graph query languages, which was sort of the motivation to have a work group on graph query languages. And this working group or this task force consists of a group of people, one half from academia, like myself, and the other half from industry, and more or less from various vendors of graph database systems, like Neo, of course, but also SAP and Oracle, Sparsity, etc. And the nice feature of that forum is that it combines practical experiences in how people use graph query languages, how we can implement systems with them. This combines this with the more theoretical knowledge from academia. So what are the complexities of certain query language features, etc. So the result of that work, so the task force worked for roughly 2 years, and the result of that work is now this graph query language proposal called GCore. And it is accepted as a SIGMOD paper and will appear on this year's SIGMOD. And if you're interested in the details already, you can go to this preprint linked here on the slide. So to explain GCore a little bit more, let's start with what is GCore and what is it not. So GCore is not a graph database system, but it's a graph query language. So it's a language specification. It specifies a syntax and semantics. So there's no system you can download, install, and then run these queries. That was not the intention. It's not commercial or proprietary, but it's a design of a query language of this mixed group of people from industry and academia, which tries to blend these different sets of experiences together in one language proposal, which we think is a good direction for graph query languages. In that sense, it's also not a standard. Doing standards is really hard and involves a lot of politics, etc. And the nice thing about this LDBC group was that we were mostly able to keep politics out of it, so really concentrate on the matter of designing a good query language. And we also didn't want it to have all possible features, but concentrate on a core of features which we think are crucial for a good graph query language. So the intention is more to provide sort of a vision where we think graph query languages that are actually implemented in systems, where those should evolve to. So what we think the future of graph query languages should look like. GCore, to get a little bit more into the details, GCore is based on the graph query, the property graph data model. We already had a nice introduction by Stefan to the query model, so I will more or less skip over that, but essentially a graph of rich objects. And when we started with the work on GCore, we sort of tried to formulate certain challenges which graph query languages face, or what we see from existing query languages. And the first challenge is that good query languages in general, so that does not only apply to graph query languages, is that query language should be composable. That means that you can take a result of one query and use that as an input to another query, as you can do in SQL ever since. But with the most existing graph query languages, you cannot really do that, or you can do it just in very limited ways. So what we wanted to achieve is what we call a closed query language. That means a query language which is, in the mathematical sense, closed over its data model. So input and output follow the same data model. And by that, your queries become composable. And then, of course, you have to see that we have certain extension points and subqueries, etc., to really make use of these composability. The second challenge which we try to address is our paths. Paths are a very fundamental abstraction upon graphs. And you want the query language to be able to reason about that and process paths. And what we see in existing query languages that you have query possibilities, but it's really hard to further process paths. And the best what you currently get is that you can sort of extract the path of the query language and then further process it down the line in your application. What we want to have is that paths should be first-class citizen in the query language and in the data model, and that's with GCore we made a proposal for that, how that could look like. And the last challenge is that we wanted to concentrate on a core for graph query language, so don't take this as a full-fledged example. There are or full-fledged proposal. There are things which we deliberately not considered because we concentrated on the core for querying. So, for instance, one thing which we not considered deliberately is manipulating the graph data. So, which is just really a query language in the core sense of querying. And what we wanted to achieve for that core in GCore is that all the query mechanisms that are defined there are efficiently evaluatable, so that you can build a system where all where the query evaluation stays tractable, no matter what query you formulate in the language. So the language does not allow you to formulate a query which is cannot be evaluated with a tractable algorithm, which is a strong theoretical guarantee which this language gives. Okay, so the main time I want to spend on is talking about the the closeness of the language and how you can use that for query composability. And the second main part is on paths. So why is query composition very important for modern query languages? Because what we see today is that a lot of data is captured either automatically or typically somewhere else. So like back in the 80s, we designed database systems, and usually the people who consumed the data were the same who fed the data into the system. But nowadays that's not the same anymore. The data comes from somewhere else. And the effect of that is that your base data, so the data which is stored in the database system, is typically has a very fine granularity, a low abstraction. So for instance, to give you an example to illustrate that, your database would store individual Twitter messages, retweet relationships, something like that. And on the other hand, when you as a user go to this data, in particular for analytical tasks, you usually talk not about these low-level concepts, but about high-level abstractions of that. Like on such Twitter data, you would be interested in communities, discussion topics, discussion threads, etc. And these are all concepts which are not in the base data. So you need to abstract from the base data to do actually things with these higher level concepts. And often you have multiple of these abstraction steps. For instance, you might define first what is a discussion group, and then you may define on the notion of discussion group what a community is, and so on. And of course, you to be able to sort of cross this concept chasm, I call it, so this division or this gap between the concepts in the base data and the concepts you want to use as a user. You need mechanisms that allow you to do this abstraction, and of course that should be your query language. And to do so, the query language needs to be composable so that you can construct or put multiple of these abstraction steps on top of each other. And if these are graphs down here, and you want to talk about higher level concepts, but also with graphs, of course you must be able to sort of create new graphs along the way. So define basically higher abstract graphs based on low abstract graphs. And that should all be doable in your query language. Okay, how can it be done in G-Core? I will use this small graph here as an example. It's basically a social graph inspired by the LDBC benchmark data. So we have people with names and employees and messages they exchanged in a forum, etc. So the details are not so important. Okay, as we have seen, to be able to abstract higher level graphs from lower level graphs, you must be able to create graphs in a query. And for that, every G-Core query has a construct clause. The other parts of the G-Core query, match and where, is pretty much like what you know from existing graph query languages like Cypher or PGQL. So it uses this ASCII art syntax to define a pattern. You can say on which graph you want to match, and you have the where clause to add additional predicates, as we have already learned from Stefan's talk earlier. So what is basically new in G-Core is this construct clause, which defines what your output looks like. And the output for G-Core query is always a graph. And what we do is we recycle the pattern syntax to also specify a pattern here, which is then instantiated for every result of the match clause. So in that case, the output would be for every match we would just output one node, and since this variable appears also in the match clause, it would be exactly the node which we have matched here, the person node. So the output graph would consist just of nodes, no edges, and they would contain all the person nodes from this social graph where the employer is ASME. Of course, you not only want to create nodes, but you also want to create edges. You can do that by specifying an edge in your construction pattern. And what this query shows is sort of a data integration scenario. So the match clause matches on two graphs, the social graph we saw in the example and some imaginary company graph. In the social graph we match persons, and in the company graph we match companies. And then we look for we do a join where the company name is mentioned in the list of employee names in the for the person. And for those pairs of companies and persons, we would create an edge between those, so that we get a graph of companies and names and edges which show who works where. And then what we could do, we could join this with the original, union this with the original social graph, so that the original social graph is sort of augmented, or that the output is an augmented version of the social graph, where we also have the company name, the company nodes, and the works at edges. But note that this query would not modify the social graph. So it's just that the output would also contain everything that the social graph contains. Then in the graph construction we can do more. So we can really create new things, new nodes, new edges. So assume we only consider the social graph and match the persons again, and now want to turn the employers mentioned in this property into nodes. Like a normalization step for graph databases you can think of. So then we could introduce a new node by giving it a variable which is not mentioned in the match pattern, and say, okay, we want to create a new node with the label company, and the name should be the names we find here in the employee property. And then we link this new node to the person who works for that company. This would give us multiple, or the problem with that query formulation is that it would give us, for every mentioning of a company here, a company node. So if two people work for IBM, we would get two IBM nodes. But of course we want to have just one IBM node, right? So this you can also do in gcore. Because you can group the creation of a graph object like a node. So you can say I want to create new nodes X, group by E, which is the employee name, right? And then you would create a new node X only for each distinct employee name. So if you have two persons working for IBM, you would just create one node for IBM. But still, those two persons would be linked with this new edge to the IBM node. So in that sense, it's pretty intuitive of what happens here. When you group, then of course you can also aggregate. So it's very simple to, for instance, have augment this company node, for instance, with the number of employees by adding a property here and with an aggregation function which counts all the sorry, it's a mistake, not all the X, but all the N. And then you would count all the persons who have this E, like the company IBM mentioned here, as an employer. And when you create multiple new nodes, they can have different groupings. And so you can also, involve with one query, compute different aggregations over different groupings. As said, you can, with the union, you can sort of augment a graph or have compute augmented versions of base graphs. With a union, you can also do that in a construct clause by just mentioning the graph here as sort of the simplest pattern you can have. So it would be the same thing. The query would compute these, or the result of the query would be the social graph union with everything which is produced by this pattern. And again, this is no base data manipulation. So the graph to which we refer here stays the same. It's just that the output of the query contains everything which also the base data contained, plus the additionally created nodes and edges. Then of course you can also query for reachabilities, as we know from other query languages. So you will use the syntax with double slashes to distinguish it, the querying for paths clearly from querying for edges. And then you have syntax as you would expect for regular path queries. So you can have regular expression over labels here to specify for which paths you are looking for. Also similar to what Stefan mentioned in his talk earlier. There is one additional thing which I want to mention is here we in the where clause we see a predicate which consists just of a pattern. And the semantics of that is that's an existential predicate. So the predicate is true if for the bound variables n and m this graph pattern exists in the graph. And since our query language is composable, we can actually define that as a syntactical shortcut of really a subquery, an existential subquery, which is shown in that on that slide. So this is the same query again, and this predicate is just a syntactical shorthand for actually having an exist with a full-fledged G-core query as a subquery, where the match pattern is exactly what we have here. So here you can see that when you define or design a query language in this composable and closed way, then you already get a benefit out of that, so that you can have special syntax without defining additional semantics, which is sort of rewriting to what you already have. Another benefit of having a compositional query language is that it's easy to define views. So you can think of that you can have a statement, create a graph view, you give it a name, and then as, and then the G-core query. And that would define you a view which exposes a graph, and the graph would be exactly the graph created by this query here. Other features we see is that you can have optional matching, so outer join semantics. Yeah. So what this query actually creates is, or when we look at the view, the graph we see from this view would be the original social graph we have seen, augmented by additional edges, where each edge between two persons have the number of messages which these persons exchanged. Like these two persons here have exchanged 2 messages, so the number is 2. And this is something you can compute with G-core queries. So let's now come to paths as first-class citizens. So the idea is basically to make paths first-class citizens is that paths also can be objects. So you can query them and then objectify them by sort of creating a new kind of object which represents that path you have queried. And when we turn the path into an object, you are also able, of course, to attach labels, to attach properties, so all the nice things you know from edges and nodes. And how would you do that? Well, you would have a match query with a regular expression again. And if you assign that path pattern a variable p, then that variable is bound to that path. And when you construct a new graph, you can include this path. And what you would get first is, of course, all the nodes and edges which the paths consist of. And then you can also say, oh, I also want to have this path object. And you do this with the letter at here. And then you are able to give this path object a label. You can say, okay, this path describes local people and it has a certain distance. Where do you get the distance from? This you do in the match clause. You can specify a variable for the cost. So when the path is matched, then this variable c here would be bound to the cost of the path. What is the cost of the path? Well, that depends. If nothing is specified, then it's just the hop distance, so number of edges. And as we will see later, we could also have a weighted cost. An additional thing of gcore is that when you query for paths, it's always shortest path semantics. That is a crucial property to make the query language tractable. So with other path semantics, you easily get a query language which is not tractable anymore. But what is possible that you not only query for the very shortest path, but for a number of shortest paths. That is also possible in a tractable way. So that you can say in gcore, oh, give me 3 shortest paths for this regular path pattern. So what this query basically what gives us is the 3 shortest paths, starting from a user named John Doe to other users that John Doe knows, or reachable over nose edges, and who live in the same city, which we have here with the extension subquery. How now can we do weighted shortest paths? So not hop distance, but is there a question?
Yeah, sorry, can you go back? So in this case, you have 3 shortest paths, and each of them has the same post, and then you create 3 new edges in the construct for each of those paths? Just to get it right.
No, this doesn't create here, this doesn't create, so the question is, if I bound 3 shortest paths, would I create 3 edges up here? First answer is this doesn't create an edge. It's with slashes, so it creates paths. And then there are 2, I tried to explain that there are 2 ways how that can happen. The first way is that you just get all the nodes and edges along these paths in your result graph. But then, so then you basically would have what makes the path, but not a new path object. To also get the path object, to be able to assign labels and properties, you have to add this add sign here. Okay. And when you have 3 shortest paths, then you can think of, you would, for one binding of n and m, you will get 3 bindings of p. So in your binding table, it would have basically 3 tuples then. Okay, so from hop distance to weighted shortest paths. For that, gcore includes the possibility to describe path macros. So a way where you specify what the path should look like. And this is done with the keyword path. And then we give this macro a name and say equals, and then come the specification of the path macro. So the first thing is, and you specify the path macro by specifying a path step. So a fixed length, or not necessarily fixed length, but in the simplest case, a fixed length path pattern from X to Y, or from some node to another node. Like in that case, it's just one nose edge, but it could be multiple of those, and also in forward or backward direction. And then you can have further constraints on these variables, and you can also specify a cost function with the keyword cost here. So that is not to be confused with the cost keyword in the match pattern, but in the path clause, the cost keyword tells us how to compute the cost. And in that case, we would just say, the cost of one of these path steps is more or less the reciprocal of the number of edges. So the more edges, the lower the cost, and the shorter the path, so to say. And when you have such a path pattern, then of course you can query again for shortest paths over that pattern. And then you would get weighted shortest path semantics. So you would actually find, in that case, all people, or the socially closest people to who John Doe knows, who have also shared an interest into the composer Wagner, in that case. So you can do with that, you are really able to express analytical queries, so to say. And here in the construct clause, what we do is we have the add again. So these paths we find are actually added as objects to the output graph. And how does that look like is that we have the original graph from the view, and additionally objects which specify us the paths we have found with the query. Okay, with that I'm more or less done. So there are what are things that we think are missing for now. Of course, to be really useful, a query language must also be able to sort of go out to existing data pods, which are usually relational data. So you want to have a way to also have relational data, tabular data as a result, to be able to feed tabular data into the query mechanisms, etc. But these are things we have discussed but not considered in detail yet. Okay, what is the takeaway? The takeaway is that G-Core is a query language proposal, first of all, which tries to propose where graph query languages should develop to, so what are desirable features, and it's designed in a way that it's closed, composable, and tractable. So in that sense, you can argue that it's well designed. It's the outcome of 2 or 2.5 years of work by a mixed group of people from academia and industry. So it really combines, and in that sense, it's sort of the first proposal doing that. It combines two domains of experiences into one design, so to say. If you're interested in LDBC work, there will be a technical user community meeting in Austin when SIGMOD takes place there in June. And these two links guide you to the G-Core paper and to a parser implementation for the query languages. And with that, I'm done, and thank you for listening, and I'm open to your questions.
Any questions, Franz?
Yes.
I think you're going to embrace interoperability, so in the future, as a future goal. I was wondering, I haven't seen anyone from Apache Tinkerbell where their claim is already to have some interoperability across some graph databases.
So the question was, why is no Apache Tinkerbell people involved? The language task force was an open community, so people were free to join, and apparently no Tinkerbell people were involved. Apparently they were not interested in. I don't know.
Then a second question. Do you think from your perspective, is there an interoperability problem between your approach and the Tinkerbell approach, like Gremlin?
I think these are, so the question is this query language interoperable with Gremlin from Apache Tinkerbell?
Yeah.
And I think this language, like also Cypher and PGQL, are sort of on a different abstraction level or have a different target than Gremlin. Gremlin really comes from a more imperative approach of specifying traverses over graphs, while here these languages come strictly from having a declarative language which builds on graph patterns, so at different angles. And for a more general answer, I would refer to a project Stefan mentioned, that there is work that tries to sort of reconsolidate these things and tries to implement Cypher on Gremlin. And if that is doable, then it would be also doable for G Core.
Cool. Thank you very much.
Welcome. More questions?
Okay, cool. Then thanks.
Thank you very much. Yeah.